Hello everyone. Today, we're going to work on a single degree of freedom tuned mass damper system and compare it to the original system. I'm going to start with a 2 degree of freedom system. You can check out the previous video to see how to build this model. First, I'll replace this transform block with a prismatic joint. To make it move freely, I'll set the stiffness to 0 and then change the actuation method to motion. Let's add a harmonic input. Adjust the unit in the converter and select second order filtering. Okay, for the input, I'll use 0.2 meters amplitude at 0.5 radians per second. And I'll make sure to turn off the external force. Now, I'll change the parameters. I've already defined all the variables, so I can quickly assign them here. Using variables like this makes the setup much cleaner and easier to adjust later on. I'll wrap this system into a subsystem. Let me organize it. And change the sensing coordinate to the Z direction. Alright, this one is a tuned mass system. Now, I'll add the original system to the model. Its parameters are the same as the primary mass in the tuned mass damper system. So I'll just copy and paste it. Add sensor here and a scope. I'll use this multiplexer to compare the results. And translate it along the X direction to avoid overlapping. I'll also wrap this up to avoid confusion. We should connect the reference here. Also, I'll turn off gravity to focus on vibration effects only. Alright, let's see the results. From the graphical plot, this one is the system without a tuned mass damper. I think this plot might be hard to interpret clearly, so let's look at the time responses instead. As you can see, both systems behave quite similarly. That's because a tuned mass damper works by being tuned to absorb vibrations at a specific frequency, typically the natural frequency of the primary system. The absorber's natural frequencies were set near the original system's resonance. Let's take a look at the frequency responses. You'll see that the system with a tuned mass has a lower peak, especially at the natural frequency of the primary system. So let's set the excitation to that frequency and see what happens. Here we go. As you can see, the system with the absorber shows a much lower amplitude, just like we observed from the frequency responses. Now let's try this frequency. At this point, the system with the absorber has a slightly higher amplitude. Here it is. Alright, let's see what happens if we apply a force directly to the primary mass instead of using base excitation. I'll move the force block to the primary mass. And this one, alright, I'm going to go with 1 Newton. And then fix the base. Let's see. you'll see that the tuned mass damper still works. It's effective as long as the excitation acts along the designed direction, whether it's base excitation or a direct force. I hope you found this helpful. If you have any questions or want to see a specific topic, let me know in the comments. Thanks for watching, and I'll see you in the next video.